Our next remote speaker is Andrea Giovini, and he received a Master in Mechanical Engineering from Sapienza University of Rome in 2001, the Master in Control from the University of Sheffield, UK in 2003, and a PhD in Control from Sapienza 2008. From 2008 to 2011, he was postdoc at INRIA Rennes, France, and since 2011, an associate professor, and 2021, now a full professor at the University of Montpellier, France, where he leads the IDH, Interactive Digital Human Group, and is in charge of the Robotic Master. And I personally had the pleasure to have him in my defense committee, which I was very happy about. And yeah, take it away.
Thank you very much, Michael. Thanks also Martina and Daniel for inviting me. I'm very sorry not to attend in person. It was quite hard for me this year for attending ICRA. So I'm going to speak about vision-based manipulation of soft objects. So what I call see and shape. And I'm going to show you some results we had on 3 different use cases, so to say. The first one is deforming via contacts with the environment, as in this photo you see, where a person is routing a cable on some contacts on a wall. The second is shaping an object while holding it with either one or both hands. And the third use case is molding plastic materials. So I'm going to present the 3 of these, starting from the first one, which will be quite short. Deforming via contacts with the environment. So this work was realized by Jiong Zhu during his PhD. He's also attending, so I say hi to him. And basically the purpose was to reproduce cable routing with our dual arm robot. So for this, we had to set up the robot in such a way that it was possible to have 2 specialized end effectors, and one for holding the cable and the other one for moving it. And here the contributions of the work, which was published in IEEE RAL, was to design what Jiong called a contact mobility index, which is a metric determining whether the cable is mobile and to what extent. And this mobility index is used to trigger the 2 phases of the manipulation, which are pulling and turning the cable around contacts, as you can see in the video. So I would call it a hybrid planning and vision-based strategy, where the planning is used to move among contacts. So the robot has a model of the contacts, but it's actually being controlled in real time according to what it sees. And in particular, when it sees the contact, it is capable of estimating this index and determining the next action to do. I hope you hear me well and that was good. So the robot you see is our dual arm robot platform Bazaar, which has been designed and assembled in our lab using off-the-shelf, I would say, robots. And you will see it a lot in today's videos because it's the platform we use in most of our work. And of course, we validated this framework in various scenarios, which are shown here. So let me now move to the next topic, which is shaping while holding. So this was also started by Jiong during his PhD, and then followed up by a current PhD student, Celia Sagur, who is obtaining nice results also in this context. I will give a short reminder of what is vision-based control for those of you who are not familiar with it. So assume we want to control this robot via some velocity in order to move its camera so that it can see the photo that you see here, the current image, in the same way as a desired reference image. So this is a classic control problem, only instantiated for the specific sensor and state space, which is camera and image space. So to do this, so to generate the proper camera velocities of a visible point, for example, you have to determine which is the reference, the target point you want to see, which is the starred coordinates of a pixel in these equations, and then you can just drive the error between the current and the desired pixel using what is called an interaction matrix, which is in a nutshell the model which relates the velocity of the robot with the motion of the pixel. So to minimize the error, the two norm of the error, one should invert the interaction matrix and multiply it by the error. So this is I would say, academic video of the kind of behavior you would get if you consider 4 pixels, as in this video, and the robot is moving in order to see them in such a way. And this framework has been very popular lately. It's also called visual servoing. So if we go back to the equation, we have 2 big issues here when we attempt to apply to soft objects. So the first one is that the task is very highly dimensioned, because the soft object has many features, possibly even infinite features. So you cannot just rely on 2 as in this example, and very quickly this leads to an underactuated problem, since our robots often have 6 or 12 degrees of freedom. And the second big problem is that if we don't have a mechanical model of the object, as in is often the case when we do manipulation of soft objects, if we don't have a mechanical model, then we cannot know the values of the matrix L and use it in our control law. So to address these 2 problems, we have reduced the task dimension using the most simple, I would say, machine learning technique, which is principal component analysis, applied on the contour of the object. And to estimate the interaction model, we have designed an observer which runs online and is updated on a short window by relying on a linear model. And basically, using this linear model, we update continuously the relationship between the robot movements and the shape of the object. The results are shown in this video, which was the result of a very fruitful collaboration with David Navarro Larcon, who is also online. So first, well, these are basics about the image processing. We need to extract a contour of the object. And in the following video, you will see in red the target contour and in blue the current contour. So here, the robot has a preliminary phase where it moves the cable around to get a first estimate of the matrix, the interaction matrix, and then it keeps on applying the visual servoing law, so inverting the interaction matrix to control the shape of the object. And the principal component analysis is run on the contour points. You can also, of course, apply it for rigid objects where it will converge more quickly. And in other situations where the object should both change pose and also change shape. So it's a more complex problem. Of course, we also had fails, which we show here, which are often related, they can be related to various issues, which we're trying to deal now with the thesis of Celia, but I think one of the main ones is that our object is not totally observable. So the natural follow-up to this, where we were working with planar objects and just using one arm in most cases, was to move over to solid objects and dual arm. So we want to control the shape in space. And we have some first results with the work of Celia. So to control a dual arm robot, we use a cooperative task representation, which is a particular type of controller where we control the absolute and the relative task. Then the rest is similar for now, in the sense that we are sampling the contour from a depth image and using principal component analysis to compress it in a dimension which is usable in the visual servoing control law. And on the right here, on the top right, you can see the 2 frames, the absolute and relative frames. So we are quite optimistic that this cooperative task framework is very useful for manipulating and shaping soft objects, because in a nutshell, the absolute task consists in controlling the pose of the object in 3D, and the relative task will mainly drive the features to give the right shape. In fact, here with rigid objects, we have mostly changes in the absolute task. This is a fancy object, a plastic glove. One thing we still have, an issue which maybe can raise questions afterwards, is that we're still only observing one side of the object because we're working with a perspective camera, even if it's a depth image. And the future will consist in having an estimator, online estimator for the occluded side of the object. Now for the last part of my talk, which is about molding plastic materials. So the first work I did on this was during my sabbatical at TUT in Brisbane, Australia. And here what I was interested in was trying to see if a robot could shape some granular material, here's some sand, to a desired shape. So the way the problem is stated is that we want to obtain a certain image, for example, here the right image from the left one. For this, we need a scalar function to measure the image error. And the robot should apply a finite sequence of actions to go from the first to the last image, similar to what Ken Goldberg presented before with the RL framework. So we assume that the method works if after ki iterations, we get an upper bound on the error. So we had to add other hypotheses for this because it's a very complicated problem and there was not much literature on it. And the first one is that the shape should be feasible. The second one is that we have a finite set of actions. Here we define two, pushing and tapping. And also the third one is that each action will only regulate some features in the image. So we can decouple the effects of actions on the state. For example, here you can see in red is the contour of our sand here, which is can be represented as a sequence of, as a list of pixels, just like in the previous video I showed you. And it can be controlled by the pushing action. On the other hand, the green is the texture of the image at a given position. So we can represent this as an imagette, a small image. And this feature can be modified by tapping on the material. So then we should design a controller based on the feature that the action affects. So recalling the actions, which are the pushing and tapping, we can rely on image-based visual serving. So I showed you the equation at the beginning. In vision-based control, the velocity of the robot is controlled by inverting the matrix which relates the changes in the image and the velocity itself. So we can start modeling this, but clearly, very quickly, we are confronted once again with an issue, which is that this model is not available and we need to find the relationship between state changes and actions. For example, if we consider the contour changes and the pushing action, we can we would like to figure out which action is needed to go from the red contour here to the green contour. And for this, there are various options. One is to go from the centroid of the red pixels to the centroid of the green pixels, and we call this method average. Another one is simply to push the sand where the distance is maximal between the two contours, and we call this method maximum. And the third one, which is quite trendy nowadays, is to use a neural network which can, given as inputs these current and desired contours, infer the blue arrow, the action needed to go from one to the other. So now the big issue is how to train such neural network, which should map the blue contours here in this image to the action, to the tool motion. So first of all, we recorded a data set of participants pushing with the tool, the sand. and the images could be easily labeled because we were using a color code, as you can see. Then we break the sequence into smaller sequences. So on the left, you see the first image, on the right, the last image, and in the middle, all the images of the sequence. And this we can do by checking when the tool stops or changes velocity. Then we can, of course, detect the contour changes between these. Red is the first, blue is the last, and green is the intermediate. And then what we can do is we can take all permutations of these of pairs of images where there has been sufficient change along the sequence. And we have all the data for this, including the labels, because as I mentioned, the environment is color coded. And this is used to train the neural network. So the ground truth will be the position of the tool before and after, and the input to our neural network as the contours of the sun before and after the action. And as you can see, we have quite good results. The yellow is the ground truth and the green is the output of our neural network, which unsurprisingly is more mistaken at the beginning than at the end of the action. Now to the funny part, the robot. So these are the experiments we did. So we want to achieve the image which you see on the top left, and the robot is operating on the bottom right and applying some pushes. Either the green or the cyan arrow are applied, and the human operator is selecting one of the two, because at this stage this was one of the last experiments we did, and we simply wanted to have fun and challenge a bit the system. So the best the behaviors that you see here are the neural network and the maximum method. So these two methods are respectively the green and the cyan arrows shown here. So more quantitatively, we benchmarked three desired shapes, which you can see here. And these are the results which our robot obtained, which are quite nice. Of course, there is a sort of a discretization issue because this is due to the fact that the desired shapes were modeled by a human, whereas the reproduced shapes are made by the robot, which has a finite tool size, and this makes the images sampled a bit. So the big problem here was to define an error metric, and for this we used the mutual information, which is a very powerful tool in signal processing and image processing because it is robust to luminance variations and generally to different environments, etc. And we compared the three methods: average, neural network, and maximum. And as you can see, in all cases, the errors converge. So the robot is making the image much nearer in terms of mutual information to the desired one. The characteristics of each method are that the average was very coarse, and in fact is the worst if you look at it in terms of error values. The neural network had a very fast convergence at the start, but was not very efficient on the small errors. And the maximum method was opposite. If you look at the curves, it takes longer to converge, but then it's very efficient on small errors, because it will keep the robot pushing where there is an error between the two contours. So after that, I extended this work back in Montpellier on point cloud shaping. So this time we tried to move in 3D and use a robot hand to do the task. So we designed 3 actions again. I mean, no, in the previous work, there were not 3 actions, but 2, but knock, grasp, and poke. And the purpose here, once again, is to predict what will happen when I apply an action. So for this, we used 3 convolutional autoencoders for the robot and 3 for the human, which could infer, given an initial shape, what would be the following shape after the action is applied. Then we want to realize the desired shape, which you see on the top left here. And for this, we do a very simple path planning through a tree of possibilities. So we simply deploy the tree from each image to all possible following images. given all the possible actions. And then at each layer of the tree, we select the depth image, which gives us the least error with regards to the desired shape. And we stop when the least error starts to increase. So one very important thing, I think, in this paper was the metric which we used to match 2-point clouds. I will talk about it right after. So this is an experiment where the robot should reproduce an image, actually not an image, a shape. So a 3D shape, given the initial point cloud, it will apply a sequence of actions to reproduce the same shape. And here you can see that the result is very similar. And then we did another experiment, which was quite fancy, where the shape was made by the human and the robot had to reproduce the shape. So again, the robot is now executing the solution which has been found in the tree exploration. And as you can see, the results were also quite close. So again, I would say the most relevant thing here is that we need a metric to train our neural networks. And this metric should be a measure of how close 2-point clouds are. So one option is to go through ICP, iterative closest point, but this is probably untractable for deep learning because it will require a lot of time to calculate the metric each time. So instead, we designed a new metric which is very fast and consists in subtracting 2 modified images and gives you immediately the distance between 2-point clouds. So I can send you the paper if you're curious about particularly this part. I will just give a few conclusions, well, a bit not directly on soft manipulation, but more on the robot learning, which we practiced a bit in, as you have seen in these works. So it's more, I would say, almost philosophical or just my own reasoning about this. And it comes from a bit of considerations on the buzz there is about robot learning and particularly deep learning nowadays. So we should keep in mind that as humans, we have developed 3 types of intelligence. The first, the most ancient one is the spatial and bodily intelligence, which enabled us to hunt and fetch our own food in prehistoric times. Then more recently, we developed the relational intelligence, which makes us relate to other human beings and interact. And very, very recently, probably in the last 2 or 3 centuries, we have developed logical, linguistic, and mathematical intelligence, which makes us solve very difficult and complex logic problems. And what I find very fancy nowadays is that with the artificial intelligence developments, we have actually we are addressing this in the opposite order. It seems like we are capable of doing fabulous things in terms of the 3rd point, like winning at Go beating at Go a human with a machine, and so on. We are starting to have robots which can interact and relate to persons, but we are really struggling on the 1st point, as you can see in many demonstrations of robots, not so as nice as expected. And this is paradoxical because the spatial and bodily intelligence are the first ones as humans we developed. So I think there's a lot of work to be done for making robots which are actually capable of operating in real environments. And this is also why molding and deforming soft materials is a very interesting problem to be generalized for other issues as well. And lastly, also another thing which is a bit of a concern with robot learning is that most of the times it operates on correlations. So you have fancy correlations as the one I show here, where you can find websites showing this. This is the relationship between divorce rate and consumption of margarine. And a computer is not capable of discerning the fact that these events are uncorrelated. And you can say the same about syllogism, such as the one you can read here. which are also logic relationship, which can easily break an artificial intelligence. So my personal take-home message, I would say, especially to the young students, is that machine learning and deep learning are really powerful tools, but they have to be used with caution. And in general, and I hope that's also what we are managing to do in Montpellier, you should combine the models with the data as much as you can. When models are available, as you saw in our work, you should keep them also in the pipeline, because data alone can be very tricky to be used. That concludes my talk. This is Bazar, our robot, and all the people who contributed to the papers and research I showed. Thanks again to the organizer.
Thank you so much. If there's any question, please go to the microphone.
Hi.
Maybe a bit closer.
Oh, hi. Thank you for your talk. For the shape throwing project, I have like a question. So I think that you have like a local reactive policy changing the shape of the deformed object. So have you observed like trap in local minimum target or some like oscillation around the target configuration of the object?
Okay, so I'm sorry, but I hear you.
Yeah, come here.
I just heard local minima on the target, but
so speak into this one.
Oh, hi. Thank you for your talk. I have a question on the shape throwing project. Have you observed like the trap of the object, like some local minimum towards the target, or like oscillation around the target configuration of the object?
Yes, for sure. That's, I think, also the reason. Well, I think you referred to the first one where we were pushing on the sides.
Yes, yes.
Yeah, so yes, as you see, yeah, there's a plateau. So somehow that we cannot go below the plateau, which is that's also why we did not expect to reach a zero error. Okay. And the reason for this, in terms of machine learning, is that I think we have the data is not, we don't have enough data for very small errors. So that could be addressed by having broader data, including very small errors, which was not present in our data set. So it was kind of overfitting and performing very well when the error is big, but then as the error is smaller, it becomes a problem. Local minima in general, yes, but we had a sort of planning strategy, as you see in the video, where we select some areas where to operate. And I think that was the trick to get rid of the local minima, because we were actually choosing some regions of interest where to apply our framework. Because if you consider the problem as a whole, I'm quite sure that, as you say, there will be local minima. So I think when you do, this is a very general answer for all of you who want to work on soft object manipulation. I think when you do soft object manipulation, you always need, so that's also why it's interesting, is that you need planning and control all the time, because for sure, your state space changes so much and your models are also changing so much that you cannot apply the controller as is. You have to control from one configuration to the other. Do you see what I mean? So there has to be a plan for going from one configuration to the other, and then a control loop below, which goes which converges to the given one. And that's been a bit the rationale of all we did.
I see. So like the planning module is kind of very important.
Yes, I think you need it very often in planning, even a rough planning. It doesn't have to be something sensational like the tree I showed at the end, the path planning in a tree, but you need that, yeah. If you want to make big changes in the object, yes.
Okay. Thank you. Yeah, thank you.
You're welcome.
Thank you very much. Let's take another question from Slido. The question is, in case of Doula manipulation, how do you estimate your interaction matrix L? And how do you know which arm contributes to the observed deformation?
Okay, so it's a similar method as before. So technically we have this 12 degrees of freedom, because we have 6 on one side and 6 on the other. But with the cooperative framework, instead of representing each arm separately, we have the absolute frame. Can you see me? You see me on the screen, right?
Yeah.
So you can have an absolute frame, which is driving the position, I would say, of the body center of the two end effectors. And then there is the relative frame, which can do, you know, the relative things between the two. So these, in any case, these are 12 velocity inputs. And then we use a principal component analysis to extract the 12 features of the object. And then what we do is that we run a few tests, just like Jiong was doing with the cable in one dimension. We run some tests to infer with linear regression the mapping between action and space. And and then this way we get an interaction matrix on a sliding window, which is updated regularly. And this interaction matrix is inverted in the control law. I hope I answered.
Thank you very much. I think we have one more question in the Zoom, and then we need to close this talk for the interest of time. Sure. In the Zoom chat, it's yeah, very interesting talk and insights. I have one question on the SANS pushing work. From what I can see from the video, there are shapes and motions in 2D. Have you considered shapes and motions in 3D?
Yeah, so in the problem statement slides, as you saw, I was mentioning a tapping motion, because we're doing this pushing on the side, and then we also wanted to tap, but it was not, so the plan was to use the texture, sorry, the plan was to use luminance texture of the images, but it wasn't working well, because I think the state was not easily relatable to the action. So that's why afterwards I moved to this 3D experiment. I think in all these sand, so in the 3D experiment, we work on point clouds and we try to do actions in 3D. But in the first one, it wasn't working well. So that's why I only showed the results on the pushing actions. This said, I think most of the problems we have nowadays, if we want to have a robot sculptor, is that the hardware of robots itself is not mature yet, because even as you saw in my last experiments, roughly what we do is we just do some fingerprints or try to grab some sand, but it's very difficult with the shadow hand or other robots to actually mold material. And I think this is a limitation of the hardware, which made us struggle a bit with actually extending to 3D. So, but surely it would be very exciting to do so. And maybe with softer robots, it could be possible, or with these robots which are waterproof, like the one which is used by Usama Khatib in the undersea, the soft hand. So yeah, that's my answer.
Thank you very much. Thanks again for the great talk.